study these things. So why study Earth materials? Well, I love these baby slides. Every one of you will use approximately 3.1 million pounds of Earth materials in your lifetime. And you can see, I see the looks, right? You're skeptical. So this goes from, the gamut. You can look at all these different things. So there's cement, sand, and gravel. You don't really think about those, right? Fuel, whatever, right? So there's all kinds of stuff on there. And I saw that you were skeptical. So I'm gonna demonstrate. How many of you got dressed this morning? Thank goodness you're raising your hands. That's good. All right, so I made this little list of all of the materials in my clothes. I looked at all the labels. So polyester, that's a petroleum-based material, right? That fiber. Viscose, that's wood pulp, so not an earth material. Spandex, also petroleum-based. Cotton, leather, right? Those are not earth materials, we know that. But all of those, to be processed from their original state into the fiber and, the shoe leather that went into my clothes, require us to use water. They require us to use machinery, so metals. There are chemicals involved in those processes that are all earth materials. Basically, if it can't be grown, it has to be mined, right? So those are all use earth materials in the processing. There's rubber soles on my shoes. There are plastic buttons on my shirt. Those are also petroleum-based. We don't get much rubber from rubber trees anymore, so we have to make synthetic rubber. I have a metal belt buckle, right? So I think you get the idea, right? None of us could have gotten dressed this morning without using earth materials. And then another example, if we think about the building that we're in, right? The building has a foundation. That's like the first thing that goes in, right? And in order to know what foundation to build, you have to know what is underneath it. You have to know whether it's soil, whether it's rock, how firm it is, right? And so the geoscientists give the engineers that information, and the engineers then design the foundation. Then when you build the building, you're using concrete block, you're using cement, there are steel girders, there's gypsum in the wallboard, there's paint. Paint doesn't grow on trees. So plastic in the chairs, right? I think you get the idea, right? So that's where a lot of this 3.19 million pounds of material comes from. So you use, all of these are earth materials. We can't do our current civilization without them. And geoscientists help us find them, get them out of the ground, and do that responsibly. All right, why study earth processes? Well, basically, because we live on an active planet. And in Pennsylvania, that manifests mostly in natural hazards like the things that are on the slide. So we have sinkholes. You're probably familiar with those if you live around here. We have landslides. We have flooding, right? Those are all natural earth processes. If we go sort of more globally, there are sort of bigger and more dramatic earth processes. So things like volcanic eruptions, big earthquakes. You may have heard on the news about the big earthquake in Myanmar just last week. Thousands of people died. All of these things they threaten human life, and they cause millions and billions of dollars worth in damage. And even those smaller hazards here in Pennsylvania also can cause casualties and can cause millions of dollars in damages, multi-millions of dollars in damages. Right? So earth processes also are responsible for creating big, beautiful things like this mountain range here. This is one of my favorite places outside of Salt Lake City in Utah. And I study Earth processes because I just think it's really cool. First of all, the processes themselves are pretty amazing. But to be able to look at a landscape like this and go back through the events that happened over hundreds of millions of years to create it. So this would have started as an ocean floor. Everything was, deposited in layers on the ocean floor. And then there was some kind of collision of plates, tectonic plates, you may have heard of those, that raised up the mountains, and then things shifted around a little again, and all those mountains got tilted in a different way. And each one of those, there's a little earthquake that helps to raise that up all the time. And then this big valley was actually carved by glaciers, and then the glaciers melted, and now people ski there. So I love being able to go back through all that and tell those stories. I'm just going to check my notes here, if you'll bear with me for a moment. And that's what really got me hooked on geology, right? It was that storytelling aspect. I'm a history buff. And to me, geoscience, geology is just like history on steroids, right? It doesn't go back 2,000 years. It goes back hundreds of millions of years or a billion years, right? So you got a lot of stuff to work with there. And my job at the Pennsylvania Geological Survey at a state, so I'm a government scientist, right? And it's really science in the public interest. I think that was a USGS slogan for a while, but I'll borrow it. Because now I get to take all these big, wonderful stories that I know and distill them down into things that are really going to help people, like help people with their everyday lives. So it's a great job, and it's very exciting. I think it's very exciting. So the title of the talk is Geosciences for the Future. So we are facing a lot of challenges as we enter the 21st century. They're not all represented here. I couldn't possibly represent them all here, but just a few of those that have to do with geosciences. Climate change, right? Finding raw materials. We're always going to need raw materials. We're going to continue to build stuff. We're going to have to repair stuff. So finding the same kinds of raw materials that we've always been using, plus maybe finding some innovative new kinds of raw materials. We need to protect our water resources. So that's going to become, water is coming under increasing pressure, but we will always need, again, drinking water, right? Water is life. So protecting those water resources and finding them is going to be important. We have to live with geologic hazards. As there are more people on the planet, people are moving into areas where they didn't live before and where things are a little bit riskier, right? Even in Pittsburgh, if you know anything about Pittsburgh, I know it's on the other side of the state, but people are living on slopes that they didn't build on before. And slopes are very steep in Pittsburgh, and everything tries to go to the bottom, right? So there's some real issues with geologic hazards. And energy sources, right? So we always need energy, and we're going to have to try to find some new sources of energy too. So all of those things are related to geoscientists. And what I'm going to do is go through and show you some examples of some of the things that geoscientists do, and a lot of those will help us to address these challenges. So one thing that geoscientists are really good at is using the past to predict the future. So one application of that is studying past climate. Why would we want to study past climate? Because if we can see what happened in the past and how the planet reacted to it, we can predict how the planet will react to changes that are happening in the atmosphere now, right? And we have all kinds of tracers in the rock record that help us to look at past climate. So this ship here is the JOIDES Resolution, and it's a deep sea drilling ship. So this was an expedition to Chile and Patagonia to actually collect sediment from the seafloor. So they drill down and they pull up samples from the seafloor. And they were looking at the composition of the sediment, which helps them to retrace what the source of that sediment was on land. And that tells about wind patterns. And wind is driven by temperature, right? So it tells about climate sensitivity to changes in carbon dioxide concentration and in the sun's radiation, right? So we can go back into the rock record, and there's a number of ways to do that, right? We can look at geochemistry, we can look at paleontology to figure out what critters were living where. So there are a lot of ways that geoscientists can help us do that. Water resources. Geoscientists look at water quantity and water quality. This is one of our geologists at the survey. Victoria's out collecting water samples from a spring. So this is a spring somewhere in Pennsylvania. I don't know exactly where the picture was taken. But some of our work involves just sort of recording data and making sure that that's available to everyone. So we have a database of water wells and springs at the survey that is publicly available. And when we find a spring, we go out and take some samples and collect some basic information, a little bit of chemistry, a little bit of physical properties that are valuable to people in understanding that as a potential water source, right? So that data goes into our database and it becomes publicly accessible. Excuse me. Raw materials. So raw materials are also a very important aspect of geological work. So stone, and as you saw, we always need stone. Stone is big business in Pennsylvania. Again, if you live in this area in Lancaster County, you probably know that there are some big quarries around. A lot of that goes for crushed stone and cement. So a lot of it is construction materials. Some of it is used for dimension stone. So that's the pretty cut stone that makes facings on buildings. So big business here. And this is one of our former interns. So I'm very proud of Liz. She actually worked with me probably about 15 years ago. And she ended up making some connections that got her into this business. And now she is the operations manager for industrial minerals for Pensy Supply, which is a big aggregate company in this area. This photograph was taken when she was pregnant with her second child. So she's a great example of how you can do a lot of different kinds of work. So geologists are important to this kind of industry because we help to find those pay zones. We help to find the rock that you want. Like if you're going to make cement, the limestone that you use has to have a very specific chemistry. And the limestone that's exposed in this part of the quarry may not have it, while the limestone that is exposed over here does, right? So the geologists help to map that out, to find it and map it out. And they also help to run the mine efficiently and to do it responsibly so that there's as little waste as possible. Another example of important raw materials are critical minerals. You may have heard of these. They're critical because we need them, especially to make electronics and batteries, and we don't have them here. We don't have good sources in the United States, and so we have to import them, mostly from China. And as you might guess, that may lead to disruptions in the supply chain, right? So there's a big effort now to find sources of critical minerals here in the United States, and the federal government is funding some of that. We get some money at the Pennsylvania Geological Survey to work on critical minerals. So a lot of that is geochemical work. We go out and take samples of rocks that might potentially be good sources and just do the geochemical analysis, make that available to the companies and the other entities that would be actually doing the exploration and the extraction. This is one of our geoscientists. This is Alex sitting at the computer. We have a scanning electron microscope here. And Alex is looking at images of rocks, polished rocks, to tell what elements and minerals are in them. So I hope that you can see, as you look at these pictures, that you can be a geologist in a lot of different locations. You can be out in the field, you can be in the lab, you can be in front of a computer doing GIS. So there are a lot of different kinds of opportunities. We also do environmental cleanup. So we not only like take stuff out, but we help to remediate the results of that. This is a photograph of acid mine drainage, because that's like the most photogenic. Many contaminants you really can't see, right? But geologists know a lot of chemistry. And so we can help to trace where the contamination goes, identify the sources of contamination, and help to clean that up. So that's a big, important function of geoscientists. This is Stephanie in her gear so that she can take samples, right? She's got her hard hat, she's got her gloves, she's got her safety glasses, so she's all set to do some work with stuff she doesn't necessarily want to touch. We do environmental restoration also. We help with that. This project actually could be the subject of an entire talk, but I can't do that here. This is the work of some of the faculty at Franklin and Marshall College, also nearby us here. So what they've done is take this pretty barren-looking farmer's field and turned it into this beautiful wetland. They removed all this sediment, which is fairly recent sediment, since European settlement, and got down to this organic layer down here. They could figure out what plants grew there because they could look at the pollen that's preserved in there. That's another thing that geoscientists do, right? So they planted the kinds of vegetation. They might not be the same because that was like glacial time. So that was, like 11,000 years ago, but the same types of vegetation. And so this wetland has been restored, and now it filters sediment so that sediment doesn't go to the Chesapeake Bay. It has lowered the temperature of the water. The water is actually cooler there, so all the critters that live in it are happier. The water quality is improved, and this wetland vegetation sequesters more carbon than this grass did. So lots of pluses all the way around there. We examine the materials on the Earth's surface. So one of the things that state surveys do is a lot of geologic mapping. So we essentially provide the data that everybody else uses. To do that, we go out and we find outcrops. So we find where the rock is exposed on the land surface, and we go out and we characterize that, we describe it, we look at, just big and obvious things like the color and the thickness of the layers. We measure the fractures. You can see that there's a lot of cracks in there. So we measure the orientation of those fractures so we can project them into the subsurface. We measure the orientation of the rock layers themselves, again, so that we can project them into the subsurface. Why are the cracks important? Well, the cracks are important if you're going to do engineering, for one thing, but also if you're looking for water resources. A lot of our water comes from groundwater, so water that's below the surface. And that water resides and travels through cracks like that in the rock below the surface. So it's important to be able to know where those fractures go, how many of them there are. Okay? Sometimes you have to get a really close look at the rock. So this is one of our interns. She's got her hand lens out, her little magnifier, and she's looking at that rock close up so that she can see the individual grains and she can describe those. So we take all of this information, we record it. We used to record it on paper in field books. Now we usually use some kind of a device, an iPad or something like that. And we bring it back into the office to make maps. So that's where a lot of our GIS staff come in. We have geologists on our staff who really just do GIS work. So this is an important aspect of geoscience work. We also need to find out what's going on in the subsurface, because it's not just water, but a lot of other things come out of the subsurface. And one way we can do that is drilling, right? We can make the map, we can stand up on the surface, we can say, well, I see this layer goes down here, and we can project it. But man, nothing beats having that sample in your hand, right? So we go out and drill, and this is the drill rig here. There's a diamond bit, industrial diamonds, not like valuable diamonds, that grinds through the rock, and you put the rods on and you drop the bit down and it grinds through the rock and it pulls up a cylinder of rock, right? And so here the drillers are laying out the cores out here on this tray so that Kristen can measure and describe, and she's got her folding ruler here that she's like holding like a staff. So that's her important tool. And this is what one of those rock cores looks like when it's all cleaned up and in its box, right? These are probably about this big around. But we have people come in we have a library of this. We have a repository. People come in and they look at these, they sample these, they can do non-destructive analysis on them too, looking at the elemental composition. So this is a great resource for people who want to come in and do various kinds of projects in Pennsylvania. One of the reasons to look at the subsurface is energy. So this is a cartoon that goes down from the surface. It's a cross-section, so the surface down to some depth, and shows the different layers where we drill wells for various commodities. In Pennsylvania, this bottom is probably about 8,000 to 10,000 feet, depending on where you are in the state. So traditionally, we took coal from up here close to the surface. We drilled for oil and gas. We still do that. Obviously, gas is a big commodity here in Pennsylvania. But there's so many exciting new possibilities for looking for different kinds of energy and different uses of the subsurface, right? People are looking for hydrogen now. That's a very new thing. But we think there are probably some sources of hydrogen here in Pennsylvania. So there's going to be geoscientists who are exploring for that. Geothermal energy is kind of an up-and-coming thing too. Our rocks are not super hot. It's not like Nevada, right, where things come, steaming up out of the subsurface, basically. But if you go down deep enough, like if you've been in a cave, it's kind of cool, right? But that's just 100 feet or a couple hundred feet. If you go below that, you go down thousands of feet, the temperature gets warmer. And so people are looking at all kinds of innovative ways to take advantage of that heat. So some of it is pumping up the liquids that already are warm. Some of it is pumping down liquid, letting it move from one well to another well and then pumping it back out, right? So you let it down there and it heats up. So there's different things that people are looking at that we can probably use here in our state. So that's really exciting too. And of course, this subsurface can be used for carbon storage. So those same rocks where the gas sat and we've pumped out the gas, the spaces, the porosity in there where the gas is now empty. So we can gasify the carbon dioxide again and pump it back down. Right? So lots of other uses for the subsurface. All right, I want to take a few minutes now to give you a little bit of history of women in the geosciences. So women have actually been geoscientists for a long time. They didn't get the respect and recognition that you might hope for in the very beginning, but they've been there. So this woman is a particular hero of mine. Florence Bascom died in 1945, right? So she was a pioneer in geosciences here in the United States. She was the second woman to earn a PhD in geology here in the US. She went to Johns Hopkins University down in Baltimore, and they made her sit behind a screen in the classroom so that she would not distract the men. I've always thought that that said more about the men than it did about anything else. So she got her PhD, and she was the first woman to be hired by the USGS. So that's a pretty impressive accomplishment there. Florence was a field geologist. There had been other women who worked in geoscience, but they were lab geologists. Women were paleontologists. There were just a few. I mean, I'm not saying that there weren't like tons of them, but the ones who had become real professional geologists before this worked in paleontology or in mineralogy. So they were pretty much restricted to the lab. Florence was a field geologist, and she went out and did field mapping, and she published maps around the turn of the century and up into about 1930 for the USGS. And I used some of her maps. I went back in my work, my first work with the State Geological Survey, I mapped some of the same areas that she had mapped. Her work was pre-plate tectonics, right? So we have a different model now, and we have new techniques. We could do different kinds of mineral work. We could do a lot of thermochronology, which means we could date when processes happened in the rocks. So we went back and looked at that again, and I went back over some of the areas that she had mapped. And they have her papers at Bryn Mawr College. She started the geology department at Bryn Mawr College. They have her papers there, and I was able to look at some of her field maps. It was great. And I could see, oh, look, I think we're seeing the same things. So that was pretty cool. But she did found the geology department at Bryn Mawr College, and she was instrumental in educating like an entire generation of those early women geologists. So she was a really important person. I especially like this photograph here because this is Dr. Bascom dressed to go out in the field. And this is what you wore, right? Women wore long skirts. They wore fancy hats. Right? So she went out like this. And, you know, there's pictures of women on horseback, and they're still like they're wearing these clothes. So it was a whole different world then. We have come a long way. Moving on a little bit, this is 1931. This is a photograph of the attendees at the Field Conference of Pennsylvania Geologists. We still run the Field Conference of Pennsylvania Geologists. I can assure you that the attendance looks very different now. If you look carefully, you will see that there are two ladies in the front row here. So there were two women in attendance in 1931. These are Florence Bascom. They were Florence Bascom's students, and they became prominent geologists in this area in their own right. So Eleonora Bliss Knopf and Anna Jonas Stows. And you can see that Eleonora is now wearing trousers. So she's at least come that far. Anna's still wearing a skirt, though. But these are some statistics. They're from an older publication, but this was the most recent report that I could find. So it goes to 2007. But you can see that if you just look at the number of degrees conferred in geosciences, that it's increasing, right, at all levels. So it's kind of on an upswing, and that has continued. So there are a lot of women now entering the field. So you're no longer going to be like me and be the only woman in the room a lot. So you have more people who have come ahead of you. And again, this is percentages of women in environmental and geoscience jobs. And again, it's sitting right around 30%. So there's still work to do, right? But but there are a lot more women in the field. Specifically looking at state geological surveys and women at state geological surveys, the first woman state geologist was Genevieve Atwood, who is in this picture here. She was the state geologist of Utah. She was named to that position in 1981. The 80s seemed to be a big sort of a blooming time for women in a lot of sciences. Before she became state geologist, she worked as a professional geologist, and she actually served for 6 years in the Utah House of Representatives. So she had quite a career even before she became state geologists. Now, currently, there are 10 women state geologists. There's a couple of vacancies that might also be filled by women. So there might be more very soon. So there's like 49 of us. Right? Hawaii doesn't have a state geological survey, oddly enough. They have the USGS Volcano Observatory, I guess, so they don't need one. But out of 49, 10 are women. So we're moving up, right? And this graph shows women who are in different positions at state geological surveys. So this is the state geologist line, and you can see that coming up. We are now up to like 20%. And everything, I can't, this is too small for me to see, and that's the science staff. There's support staff and science staff, right? So the science staff is this red line, and you can see that is also going up. At our survey here in Pennsylvania, we have 60% women on the staff. And most of those pictures that I showed you were pictures of our staff at our survey. So you will not be alone should you decide to pursue this as a career. So I think that's the end. So I hope that you got a little bit of a taste of what it's like to be a geoscientist. Like I said, you can do it anywhere. You don't have to be outside hiking around if you don't want to be, but you can be. And if you're interested in finding out like what the geology is below your feet, you can go and visit our PA Geode site. This is an interactive map. You can, drop a point and find out what the geology is. And there's a lot of other different kinds of layers on here if you want to explore that. So thank you.
Thank you so much, Dr. Blackmer, for sharing your expertise and your knowledge. I know what website I'm going to visit today for sure. You know what is really interesting is there's such a broad area that touches so many aspects, but in particular, the forensic nature of it that we don't often think about. Like you were mentioning, and we discovered this using the pollen. That was just, so many amazing things. All right, so at this time, before we go to our first session, we're going to take a few questions from our audience for our keynote speaker. Let me know, just raise your hand if you have any questions, and I'll come by with the mic. Love it. Yes.
What would you say is the difference between geoscience and environmental science?
So geoscience involves some more specific disciplines than environmental science. And so you would study mineralogy, which you might not get in environmental science. You would maybe do some more geochemistry, but there should be a lot of chemistry in environmental science too. You would study structural geology. So looking at the way faults work, the way stresses work in the Earth's crust, and perhaps very importantly, if you want to do professional work in geology or in geoscience in many states, you have to be registered as a professional geologist. And most environmental science courses or majors don't include the appropriate courses that you need to get a professional geologist license.
That's a great question.
Hi. Other than taking Earth and Space Science classes, do you have any recommendations for middle school or high school students on how they can get involved in this field, maybe extracurricular things?
There are a number of like rock and mineral clubs and other sorts of hobby groups in the area. So that might be an opening to get involved with some professionals and some amateurs. It's a mix, right? But the amateur people know a lot because, if you're passionate about it, right, you're going to learn a lot. So that's one way. We do a lot of programs. We don't have a high school internship program right now. We have had that in the past, but we're not running anything like that now. But I would say look for different events like that. The state parks sometimes have events that will have people attending that do, fossil collecting or different kinds of activities like that too.
You're right. It's interesting. The amateur clubs, they know so much because they were so passionate about it.
They know more than me.
I wonder, yeah, they were just. Thank you. You're both smiling. You're the one. Okay. Great. Yeah.
Hello, my name is Hasset. It's nice to meet you, Dr. Blackmer. So in regards to hydroelectric power, do geologists work closely with other scientists, like sciences like physics and stuff? And could you briefly describe the process of hydroelectric power and like how you guys work with other sciences?
Yeah.
Okay. So the principle behind hydroelectric power is that you have moving water and you use the moving water to generate electricity, right? So you turn a turbine with it or something like that, and that generates the electricity. You have to usually build a dam to do that. And you'd need to have geoscientists to help, again, like do the foundation work. So you'd want a geoscientist to come in before you started construction so that you could understand the foundation of your dam, right? What you're building it on. There have been a lot of issues with people building dams where they should not have built dams. So that may be the major interaction for hydroelectric. We don't get in so much into like examining the effects on the aquatic life or anything like that, but we can help to understand, like you build the dam, obviously you back up water, so what the implications of that are going to be. I think that our or a geoscientist interaction with that would be sort of before the fact, and then in like helping to maintain the physical infrastructure, right? Not in actually generating the electricity. That's an engineer's job. Sure.
In regards to your career with the public interest, how does that affect like the aquatic life or like the dam being built in places that it's not supposed to be?
Again, that's not necessarily our part of the group, but we have gone, not necessarily us, but there are public meetings and things where you might have a geologist present to help answer questions about things like that. And a lot of the engineering firms have geologists who work for them. They don't listen to them as much as I would like them to, but engineers tend to think that they can do things on their own without the geologists, and sometimes that gets them into trouble.
Any other questions?
Hi, I'm Sona. I wanted to ask, you mentioned earlier about like the public interest and kind of imports that come in for raw materials where we wouldn't have access to them. Does any like ethical obligations ever fall on like the geoscientists to kind of ensure that those raw materials are coming up in ways that wouldn't negatively impact the environment around them or like any of the people that live in those environments?
Yeah, we understand a lot more now about the environmental effects of extraction than we did in, like the 1930s or the 1950s or something. And we geologists, geoscientists of various kinds, do play a part in ensuring that extraction is done responsibly, right? So we understand the geochemical interactions as you extract something. This is a big question. First of all, you can't get any of this stuff. Like, you can't generate energy. You can't get the minerals that we need without pulling them out somehow. So we have to do some kind of mining to maintain our culture the way it is. It's just a fact. And you can't do any of that without having some impact, right? The house that you built, you dug a hole, and that had an impact on the environment, right? So you can't do anything really without having an impact. But you try to do that responsibly, and you try to minimize that impact. And so there are a lot of ways that companies try to manage their waste, right? And there are responsible ways that have been developed to do that. Some companies are more responsible than other companies. And a lot of the issues that happened in Pennsylvania at the beginning of the gas boom were not related to things that were happening underground. They were related to waste disposal on the surface, because the companies weren't used to our geology, basically. They were from Texas. The situation is very, very different there. And they didn't listen to the local geologists. Not a single gas company came and talked to us about what the Pennsylvania geology was like, right, before they did that. So if you have a geoscientist looking at the whole process, they can help you to understand what kinds of, let's say, nasty things in the waste are coming up, and the kinds of reactions that might happen between the chemicals in those wastes and like rainwater or oxygen in the atmosphere or the surface, whatever is the soil on the surface. They can help you understand that, and then you can design a system that mitigates that, right? So we have an ethical obligation, right, to be as responsible as we can. Does that answer your question?
All of them were. And I think I'm just looking at the time. Does anyone have any other question? I think we might have to limit it to one more if there is a question. Yes, where am I seeing the hand? And why? Yes. Thank you.
Hi, I wanted to learn more about how did you decide geology? Was it something that you always wanted to do, or yeah?
Yeah, I've always been a geologist. I think ever since I was a little kid, I debated whether to put the slides in, and I took them out. But I remember when I was like 8 years old, sitting on the floor with the ocean floor maps from the National Geographic magazine. You don't remember any of that. But my parents got National Geographic, and they had always had maps folded up in them. And in like 1968 and 1969, they published ocean floor maps, which were the first view of all of the like huge mountain ranges and trenches and things on the ocean floor. And I found them, and I used to pull them out. And when I was 8 years old, my mother was getting me pamphlets from USGS. So it's just always been a fascination for me. I went to college to study geology. Most people don't do that. Most people fall into it. I was just talking to some friends of mine. I was at a conference, and we sort of went around the table at dinner and did the how did you get to be a geologist? And everybody else came to it from some like, oh, I happened to take this intro course and it was awesome and I was hooked, right? Or, you know, there's all these different paths that people take. So that's the normal thing. But I don't know. There's just something in my brain that clicked with it. It's history. It's the natural world. It's being able to tell those stories. You know.
So it's thanks to your mom. She got you the National Geographic, and I'm always taking any opportunity to be like, and thank you, Mom. All right. I think at this point, you are welcome to go to your next session. It is such a pleasure to see all of your faces, and I hope to see a lot more. Thank you, everyone. You guys are